Okay, today we talk about DC machine, right? DC machine or direct current machine. And the DC machine can be both DC generator, and DC motor, right? DC motor. So this machine have two important parts, which is the rotating part here. Rotating part is usually the coil wound into the cylindrical shaft, okay, and the cylindrical shaft here. And another part is stator. Stator can be both permanent magnet field, or it can be the field that generate from the electricity also, right? It's a magnetic field to produce this to produce the magnetic field. Okay, here. So in this example, the direct current machine have rotor with the coil, right? With the coil. And the stator is the permanent magnetic. Yeah. Yes, for example, yes, the magnetic field to generate the magnetic field. So if we put the coil or the conductor in the magnetic field, right? If we move the conductor, we can get the current, right, from the rod of electromagnetic. And or if we supply the current to that conductor, the force will apply to that conductor, right? That you have to learn in the physics course, right? If we supply the current to the conductor, and then if the conductor is placed in the magnetic field, right, it will have the force, right? So in that case, it will act as the motor. Okay. So if we supply the current, right? Supply the current to the coil. Yeah. It will move, right, due to the force applied to the current flow by the right hand rule, right? F is IL cross B, right? B is the magnetic intensity density, right? Flux density. B is flux density, right? B is flux per area here. Right? And to supply the current to the moving coil, usually we have to do pass to some special device called commutator and brush. So we have commutator and brush here, right? Or sometimes we call slip ring here, right? Commutator and brush, right? To supply the electricity to some moving part, right? It's attached together, right? And it's moved, right? And this part, usually we use this symbol. Then it is a symbol of carbon brush and slip ring or commutator here. Okay, this means that we supply, this is moving part, right? And we can supply the electricity. Okay, and you may have some laboratory on DC machine, right? And you can see the carbon brush and commutator. So how we supply the current to the moving part here. Right? And if we use it for a long time, this will have some we have to replace, right? We have to replace this part, right? Carbon brush here. Okay. Okay. And for another side, so in the upper photo, it is the permanent magnet here. This is permanent magnet. Right? And on the other hand, we can generate the magnetic field by electricity here. Okay, if we put the coil, right, like this, we can generate the magnetic field, right? Here. And we call this part as the excitation current, or IF, or field excitation, to generate the field, right? So this circuit is the circuit for the field generation, right? To generate the field. Okay, and the rotor is here. Okay, so the coil in the rotor usually we call armature. Armature. And the coil that generates the field we call field excitation. And so we have two electricity part, field and armature, right? Armature is the main coil. If we generate the DC electricity is generated from this, right? From this main circuit, right? And this is in fact the purpose is to produce the magnetic field, right? The magnetic field. So if we use the electricity to generate the field instead of permanent magnet, there is one advantage that we can control, right? We can control the magnetic field by density. We can control how much we want for to generate the field, right? And if we use permanent magnet, so we cannot control, right, for the magnetic field intensity or density. Yeah? So, yeah. So we have two parts, right? So this is the commonly used DC machine. Usually we have field excitation and armature, right here, armature conductor and field excitation. This is two important parts, and in we can write the circuit in this symbol. This is field excitation, right? This is field excitation coil. This coil to generate the magnetic, and this is armature coil here. Armature coil is here. Sometimes you can write out this. The coil is here. Okay, and this is moving part. Okay, this is moving part. Okay, then the field coil also have resistance, and the armature also have the resistance, right? Both also have resistance. Okay, so in this form we call separate excite. So if we use this machine as the motor, we need to have two sources. Two sources mean one DC source for field excitation and another one DC source for armature, right? To make this machine move, okay, we need to supply field excitation and we need to supply the current to the armature, right? So we need two sources, VF and VA, right? Field excitation and armature voltage. We need to supply two sources to make this motor move, okay? To make this motor move. So we call this type of DC machine as separately excite, separate two source, right? We separate two source. The excitation is separate from the main power. Okay, the excitation power is separate from the main power, so we call separately excite. We have non-separate also, right? I will talk later. Okay. Okay, this is separate excitation, and there is many ways to supply the voltage and current to the DC machine. So instead of we supply into source, we can connect these two circuits together. Okay, for example, we can connect this circuit in parallel. We connect to this. We connect to this, and we supply it by the same source. Okay, we supply by only single source. Okay, we have single source. With this connection, we call shunt connected here, right? shunt connected, connect in parallel. So the current flow here will flow into two-way, right? IA and IF here. Okay, this circuit. So we analyze DC machine by with shunt connected by this with this circuit, right? Okay. Another way to connect these two coils together is connect in series connected. So we supply the voltage to field excitation and then in series with amateur, right? Here. This is in series form, right? We call series connected. Okay. So in this case, IF and IA is equal to each other, right? Supply the same. Okay. Or we can have two field excitation. Two field excitation. We have one shunt winding and series winding. Okay. For field excitation, we have two field excitation also. Right. We call this type of machine as compound machine. This is compound machine, right? And compound machine can connect in two ways, right? Yeah. First is short shunt compound connection. Short shunt is shunt and then series. Okay, shunt together, shunt with the armature and then series with the series winding. Another way is long shunt compound machine. It means that we connect the series excitation first and then this circuit in parallel to the shunt winding. Okay, and we call long shunt compound connection. Okay, so many ways to connect the circuit, right? Many ways to connect the circuit. Instead of using separate excite, okay, instead of using separate excite. Okay, so in DC machine, the field excitation that provide the magnetizing current is occasionally provided by the external source, right? We call separate excite here, right? We have to supply both field and armature here, right? And more often, the field excitation is derived from the armature voltage and machine said to be self excite here, right? Here is self excite. We call self excite. Sometimes, if this is the generator, the voltage that generates from the generator will supply to the field excitation itself. We call self excited, right? Okay, self excited. The later configuration does not require the use of separate source, right? Here. So in for cell excite, we don't need the separate source, right? For field excitation, right? And if a machine is in separately excited configuration, an additional source VF is required, right? As I have told. Okay. In the cell excited case, right, one method used to provide the field excitation is to connect the field in parallel with armature, right? Here, this is in parallel, right? Or we call shunt connected, right? Since the field winding typically has significantly higher resistance than the armature winding, this is high resistance, right? High resistance than armature circuit, right? It should not draw excessive current from the armature. So most of the current it flow in this part, right? Small current flow in this part, small current, and this is higher current here. Okay. Further, a series resistor can be added to the field circuit to provide means for adjusting the field current independent of the armature voltage. This configuration called shunt connected machine, right? So we can use this resistor to adjust the field current, right? We adjust the field current by adjusting this variable resistor here. Okay. Another method is to connect the cell excite machine by in series form, right? This is the series. This we call series connected machine. Right? In this case, the field winding will support entire major current, and thus the field coil must have low resistance. So this usually have the very low resistance. This type of machine will have low resistance uh, field winding, right? Low resistance field winding. Yeah. Otherwise, it will produce too many loss, right? Okay. This configuration is rarely used for generator, since the generator voltage and the low voltage must always differ of the voltage drop, right? It's not uh, it's not good to use this type as generator, and we use usually we it's very difficult to control the speed also in motor for motor. But the advantage of this machine is it can produce a very high torque, high starting torque, right? And it's usually is used as the car engine starter. Okay, car engine starter. When you start the engine, when you start the engine, you need to produce the first rotating, right? Long times ago, we need to move by hand, right, to start the engine, right? Right. But nowadays we just turn on the electricity, right, supply to this motor in your car, right, in the car, right, to start the engine, right? This type of motor, right? Okay. And it have a very high torque, right? It can pull uh, entire car, right? It can pull the car. But only in the starting time. After start, the torque will drop really fast. Yeah, right? Okay. This and this configuration is rarely used for generator. It can generate voltage and low voltage, but differ by the voltage drop. Voltage drop is very much. Okay, and uh, then series connected motor are commonly used in certain application, right? Yeah. And the third type of DC machine is compound connected. So this type of machine have both series winding and shunt winding, right? This is a short shunt connection, and this is a long shunt connection. You connect series first, then connect the shunt winding. Okay. Okay, now we come to some analysis, right? If you have the DC machine model, the force on the Y is given by this expression, right? F equal to IL cross B, right? It's a vector, right? Yeah. If the current flow in along the line, right? The conductor, along the conductor, right? You have the force applied to this conductor. It's removed, right? It's removed. Okay, and the torque for multi-turn coil, we can use this equation is KBI psi alpha. Right? Alpha is the angle between flux density, right, and the normal to plane of the coil, right, to the plane of the coil. It's the angle for the torque, right? Okay. Then a field excitation is exhibition. A magnetic flux is generated by this current, right? Okay. We have few important equation to analyze DC machine, right? If you just try to understand how to use this this field equation, this will be fine for you. Okay. So in case we assume by virtue of the commutator, the torque angle is gamma here or alpha here. It's keep very close to 90 degree, right? And sine gamma will be 1. Okay. So in this case, the torque will be K phi I. K is constant. Okay, for the machine constant. Okay, K phi I. And the mechanical torque is P is omega T, right? Oh, sorry. Mechanical power is torque into omega, right? T omega. Mechanical power is omega M into T torque, right? And we substitute T by K phi I, right? We can have omega K phi I is the power, right? And if we not consider the loss in the machine, so we can have EB, right? Electric power E and IA equal to omega M KT phi IA, and we can cancel IA. We can have EB is K phi omega. EB is K phi omega. K is constant. K is constant. Okay. EB is the voltage. Voltage. So in this case, we have like this. In this part, right? And we have field excitation, IF, right? Field excitation, or this can be all permanent magnet, right? This magnetic field part, right? Produces by IF, right? Produced by IF. If this machine is the motor, when we increase the voltage, EB is, if we increase the voltage, the flux is produced by field, right? It's produced flux here. If we supply more current, we can get more magnetic flux. Okay, you got that? So this is supplied by field excitation, right? Flux is depending on the field excitation. Okay. So if we increase the voltage supply to this type of motor, what happens? If EB is increased, right? If the flux is constant, K is constant. If we increase the voltage, the terminal voltage, what happened to this machine?